Hello, I'm Fergus McRae, a third year geophysicist. My presentation will describe the dissipation of strain energy in a strike-slip region and its connection to the earthquake cycle. This is a brief outlook on the key parts of the talk and how long they will take. So, why is research into strain important in faults and earthquakes? So here we see a stress map from the San Andreas Fault region. This is a region where the North American plate and the Pacific plate come into contact, creating areas of high stress. By looking at crustal velocity, which was measured using GPS systems, we can see the two main areas of stress, the San Andreas Fault and the Eastern California Shear Zone. The reasons for these areas of high stress are debated. However, understanding them is critical in understanding the role of earthquakes and to better predict and understand their models. And we can do this by various geophysical and geological techniques. In this presentation, we're going to focus on the use of structural geology of shear zones and faults to understand crustal deformation and strain dissipation, which results from stress buildup. So now we're going to ask some fundamental questions to the rest of the talk, which is what is strain and stress? So stress can be defined as the force applied per unit area, as we can see from figure 2. And there are four principal stresses. There are compressional, tensional, shear, and confining stress. Compressional stress is pushing rocks together. Tensional stress is the lengthening or pulling apart the rocks. Shear stress is the stress that acts parallel to the cross-sectional area of the rock. And confining pressure is just the lithostatic pressure, which is the pressure applied by all the rock above, balanced by the pore fluid pressure within the rock. And now we can ask, well, what is strain? Strain is the resulting change in material shape or volume due to stress and can be visualized as deformation. And there are three possible responses to an increasing stress, which is either elastic deformation, plastic deformation, or fracture. And now we're going to look at what is a strike-slip fault. So Fossen defines a strike-slip fault as faults where the displacement vector is parallel to the strike of the fault. They are hence areas of high shear stress. And we can describe them using principal stress axis, or Anderson's classification, which we can see from figure 4, where sigma 1 is greater than sigma 2, which is greater than sigma 3. And we can consider strike-slip faults orientation, which is whether they're synstral or dextral. Synstral refers to left lateral movement, dextral refers to right lateral movement, shown by figure 5. So, finally we can ask what the earthquake cycle is. And the earthquake cycle is a simple term for a two-phase process. Phase 1 is the accumulation of elastic strain with tectonic loading. And we can see this by the increase in stress. And the second phase occurs when we have a certain amount of elastic strain energy stored, which overcomes the strength of the rock that is resisting fracturing. The rock then fractures, releasing this stored energy. And we can see here. Now, what we notice is the timescale of the cycle is dependent on many factors, like fault maturity, structural relations of the fault zone, and the fault strength, which can vary with space and time. As such, we need techniques from many disciplines to model earthquakes. So we see here an idealized model, and we see here the natural faults, and you can see how the geological time changes, the amount of stress or strain, the amount of stress needed changes, the strength of the rock changes, so it can be very hard to model. Now we talk about strain dissipation within a strike-slip region. And as we referred to earlier, strain can be dissipated in three fundamental ways: elastic, plastic, and fracturing. And we can relate these to different regimes in a transcurrent strike-slip fault. There's the brittle regime, the ductile regime, and the brittle viscous transition zone. And each regime has different deformation characteristics and different strain dissipation. However, most share an area called the fault core zone, which can be millimeters to meter scales, surrounded by a damage zone that makes up the fault region, which is meters to kilometers scale. And as we reach higher temperature gradients, they kind of form a more shear core zone and it widens. And we can see this depicted by figure 8, of the widening at the shear zone. And they don't give a scale here, but the MOHO depth is between 25 and 60 kilometers. Okay, so the brittle regime is usually the upper 10 kilometers of the crust. The segment between 3 kilometers and 10 kilometers is known as a seismogenic zone, and this is where earthquakes can nucleate. We can better understand this region by looking at exhumed brittle zones, and they show formation of certain rock types: cataclasites, fault gouges, breccia, crust breccia. And we can see this from figure 8 here, which shows, the classification on large class or millimeter scales, and how fine-grained the matrices are, and if the rock can be foliated or not, or if it's cohesive. And cohesive just refers to how bounded the rock is. A non-cohesive rock is not very bounded and can fall apart easily. And these rocks show signs of brittle deformation mechanics, like progressive fracturing of rocks and frictional sliding. However, we also see signs of more ductile deformation mechanics as well, like granular flow and pressure solution creep. And granular flow is the movement of grain boundaries with little or no breaking of material. However, it doesn't occur at higher confining pressures. And pressure solution creep is the transfer of material by dissolution of a soluble species along grain boundaries into areas of low confining pressure where they can be deposited. This is just an example here of some cataclasites, and then the fault gouge running along the middle here. And what we find from this brittle zone is that it can be depicted by Byerly's law, which relates shear stress and normal stresses. And it says that when the shear stress gets really high, the normal stress gets really high, the shear stress becomes independent of the rock type. And the brittle zone usually shows relative fast strain rates of around 10 to the power minus 7 per second. So our next section is the frictional viscous transition zone. And this is the intermediate zone where we have some brittle and some plastic deformation. And it can be recognized by still having some cataclasic rocks and cytoseculites, but we also see a new rock type called mylonites. The myelonitic rocks are created when pre-existing textures of original rock are broken down and transposed. They are extremely fine-grained and have strong lineations and foliations. Now, the final zone is the viscous or plastic regime. And in this regime, the temperature pressure gradient allows the flow of material by dislocation creep. And it contains mylonites, which they show simple shear or subsimple shear indicators, and are usually very ductile. A brilliant diagram for describing all these features together and what occurs with one earthquake cycle can be seen from Handy, Hirth, and Hovis. And this figure here gives a clear picture into the interconnected nature of the three regions and how strain is accommodated all throughout the strike-slip fault zone. And we also recognize that the regime where the most strain is accommodated can heavily impact the earthquake cycle. If most strain is accommodated in the brittle regime, we would expect more frequent earthquakes. However, if more strain is nested in the ductile regime, we might expect more aseismic deformations. And this will vary with space and time along the fault zone. So here we see one earthquake cycle from T1 to T2 and T3, and we see how it changes the deformation type in the fiscal transition zone and the strength of the rock here. So looking to summarize here, we can conclude by acknowledging that strain energy is dissipated differently throughout strike-slip faults, not only in space but in time, and that many control factors such as rock type, temperature, pressure, fluids present, deformation type, and history can all impact earthquake nucleation and cycles, and that greater research into which zones have the largest impact is very important. Some theories have even theorized that the fiscal transition zone can create stress drops which cause earthquakes in the brittle regime. And this is just my references here and here. And thank you very much for listening.